So at this point, we are still working on section 1.5, probability of intersections, and we were using tree diagrams. So for example 12, we have a manufacturer of 27-inch bicycle rims has determined that a rim may have 3 types of defects. The diameter is not within specifications, the holes for the spoke attachments are not evenly spaced, and the rim has a visible flaw. Okay, these types of defects are assumed to occur independently of each other. Based on past inspection data, 4% of all the rims have a type D defect. So we have the probability of a D defect is 0.04. 2% have a type S defect, so the probability of S is 0.02. And 6% have a type F defect. A rim may have more than one type of defect, and we know that they all happen independently. So what we're going to do is we're going to draw a tree diagram. So what would happen is we would look at the bicycle wheel and we would first check and see, do you have a certain kind of defect? So they don't have to be in this order, but let's say they check for the D defects first. Okay. So your choices is you can have a D defect or you can not have a type D defect. I'm just going to call it not D or ND. Okay. What is the probability of getting a D defect? It is 4%, 0.04, which means the probability of a not D defect would be 96%. Now, whether or not you have a type D defect, can you still have a type S defect? So we have S or not S, and then even if we didn't get a D defect, we can still have S or not S. Now, what is the probability of getting an S defect? 2%. Now, did they say anything about the probability if you already have a type D, then the probability of S is this, or if you don't have D, then the probability of S is this?
They have more than one at the same time.
Okay, they said more than one at the same time, and they said that they are independent of each other, which means it shouldn't matter which branch I'm on, the probability of getting an S should always be the same. It's not affected by whether or not you have a type D defect. So the probability of S is, what do we say, 0.02? For every branch, it will always be 0.02 because they were independent. So your probabilities aren't affected based on which branch you're on. Okay. And then the probability of no type S defect would be 0.98, 0.98, using the complement rule in there. And then finally, we need to look and check and see if they have a type F defect or not. And the probability of F is always going to be 0.06. And then, of course, the probability of not getting a type F would have to be 0.94. And then what did we do last time with our tree diagrams? Remember? We wanted to find the probability of each of the intersections. So to do that, I need to multiply along each branch to get the probability of my intersection. So 0.04 times 0.02 times 0.06 is 0.00048. So the probability that you get a type D defect and a type S defect and a type F defect is 0.00048. Okay. We need to go through and do that for each of these branches. So you guys on that half, go ahead and take like the next two probabilities. You guys here take the next two. You guys take the next and start punching them in so you can tell me what they are. So I guess that you guys take the set here, the middle, take this set, and you guys take this set, and I'll do the last one on the top. Okay, so anyone have the next branch for me?
Next one should be 0.002352.
Like that? Okay, the next one?
0.0368.
Okay, the next one?
001152.
The next one? Sorry, say the last part again.
0.018048.
Okay.
0.056448.
And the last one?
0.884352.
Sorry, say it one more time.
0.884352.
Okay. So we have all of our probabilities for all of the intersections. If we added all of these up, and I wrote them down correctly, we should add them up to 1. Okay. But that's what our tree diagram looks like, and it's useful to have this because now we can go through and find various other probabilities that I might ask. So let's see what it actually wants us to find. So using our information, what percentage of all the rims that are produced will have only a type D defect? Okay. And this is useful because we have listed out all of the options. Okay. So we can look back up and say, okay, well, which one of these things have only a type D defect? Okay, so we know that we need the D. Okay. And then do I want to go up or down on my branches? Down, so we can't have an S, and then down again because we can't have the F, so that's going to put me at 0.0368. So that's my probability of getting only a type D defect. And that's the only outcome up there that corresponds to it. So since it asks for the percentage, that would be 3.68%. So 3% of the bikes have only a type D defect. So the next one, what is the probability of getting a rim with exactly 2 defects? So for this, I'm going to go up and look at it and see which ones have exactly 2. Okay. Does this one have exactly 2? My first one. Okay, what about the second one? Okay, third one? Let's see, 1, no, 1 more, so yes. Okay, this one? Let's see, that's only 1, so no. The next one? Okay, next one? Next one? And the last one? No. So, what do I have to do? Just add up those probabilities. Okay, Okay, someone will have to read them off to me. I can't see them all at the same time.
It's just a 2, right?
I think I saw 3.
So we get 0.004255.
Oh, that's what you get if you add them all up.
Yeah.
Okay. What do you, just read off the 3 so I can write them down, what 3 we had to add up.
000752. 002351. And 001152.
Okay. So we just added up the probabilities for each one that we were interested in. And finally, we have that one finished rim is to be randomly selected for inspection. What is the probability that the rim will have at least one type of defect? So we want at least one type of defect. So how could I do this? Okay. Use the complement rule. The 1 minus. Okay. Could I do it without the complement rule? What would I have to do if I want to do it without the complement rule?
Add them all up.
Add them all up. So everything that had at least 1, which would be the top 7, yep, I would have to add up all those probabilities. Or I can use the complement rule. Because the complement of at least 1 is none. So the probability of at least 1 equals 1 minus the probability of none. And the probability of none was the last branch, so 0.88435. So 0.11565. So questions on that tree diagram. Do you feel like they're useful? Some people like them, some people don't. So for our next example, we decided to draw 3 hearts, 3 cards from a standard 52 card deck without replacement. We are interested in determining if the cards are hearts or not hearts. Now, do you think these should be independent or dependent events? Because, okay, since we don't put the card back, the probability change, so these are dependent events. Okay. So we draw the tree diagram. So I say, okay, well, on my first card, my 2 options are hearts or not hearts. Okay. What is the probability of getting hearts on your first draw? Okay, 1/4, or I'm going to just write it as my 13 out of 52 to start with. And then not hearts would be 39 out of 52. That's for my first draw. Now let's look at my second draw. I can still get hearts or not hearts, or hearts or not hearts. Now if I drew a hearts card the first time, now what is my probability of getting a hearts the second time? 12 out of 51, because I already drew out 1 heart, so there's 1 less hearts and 1 less card overall. Okay. What about not hearts? How many not hearts are left? Okay. Okay, let's see. So for my not hearts, there's still 39 not hearts, because I didn't draw any not hearts yet. But there's still only how many total cards? 51, because I still drew 1 card out regardless. Or, what do you remember about these 2 probabilities on the branch? They have to add up to 1. So 12 plus 39, that does give me 51. So 51 out of 51, I'm good. Okay. Now let's say we drew out a not hearts card on our first draw. How many hearts are left to choose for the second draw? 13. How many cards are there? 51. Now I drew out a not heart card, so how many not hearts are left? 38 out of my 51. And I am going to alter this and say, let's just say we drew 2 cards, just to save us a little bit of time. Okay. So now what am I going to want to do? The probabilities of the intersections, multiply along all of my branches. So if I multiply along the first branch, that's the probability of a heart and a heart. So 12 out of 52, or 13 out of 52 times 12 out of 52, 51. 0.0588. My next branch, so the probability of getting a heart and then a not heart, is my 13 out of 52 times 39 out of 51. .1912. My next branch, so I need a not heart and then a heart. .1912. And my last branch, the probability of a not heart and then another not heart, .5588. Okay. Anyone get anything to disagree with me? So that's my tree. So the next question asks us, what is the probability of getting exactly one heart? So we just need to look at it and say, well, which of these things have exactly one heart? So does the first branch have exactly one heart? Okay, what about the next one? Yes? Okay, what about the next one? Yes? What about the last one? No. So we just add up the probabilities that did have exactly one heart. So we have 0.1912 plus 0.1912. So 0.3824. And then for our last question, let's ask, what is the probability of getting a heart on the second draw? So again, we're just going to do the same thing. We go up and we look at our intersections and see which ones had a heart on the second draw. Okay. Do I want my first branch? Yes, I had a heart in the second draw. What about my second branch? No. Third branch? Yes. Fourth branch? No. So we have 0.0548, was that right? 88. Plus 0.1912. 0.25. Questions on this? Then let's move on to section 1.6. Posterior probabilities is what our book calls it. Usually we call it Bayes' theorem. There's actually a whole bunch of statistics that revolves around this one section. So example 14. It is estimated that 0.6% of the American population has the HIV virus. A diagnostic test is used to attempt to detect whether a person has HIV. According to historical data, 99.9% of people with the HIV virus receive a positive test result when they take the test. Okay. And then we also know that overall people get a positive test result 1.6% of the time. So the first thing that I like to do in every problem is start writing down what they gave me in my probability symbol so I know what I have to work with. So 0.6% of the American population has the HIV virus. Okay, how do you think you might want to write that? So the probability of HIV equals 0.006. So that's just the overall probability that someone has HIV. Let's see, then we get to 99.9% of people with HIV receive a positive test result. What is that telling us? Okay, so you said probability of positive and HIV. Anyone think anything else?
Positive given HIV.
Positive given HIV. So it is a conditional because it's saying we already know they have the HIV, then the probability of getting a positive. So the probability of getting a positive test result if you know they have HIV is 0.999. That sounds pretty good, right? How many of you guys would feel comfortable with the test with that accuracy? Okay. I hopefully you don't have HIV, but if there's any other medical test, that sounds like a pretty good accuracy, right? And then let's see, we know that overall people get a positive test result 1.6% of the time, so that's telling me just the probability of positive overall is 0.016. Okay, so we can find a couple different things. We know how to do quite a few different things with this data. So like, what is the probability that an American has the HIV virus and they get a positive test result? That's asking me for the intersection. So we want the probability of HIV and positive. Do you have a formula for the intersection?
The given the equation, the given equals the intersection over.
Okay. So we have a probability for the conditional equals the probability of the intersection over the probability of the given, okay, which we rearrange to get our multiplication rule. So we know that if we want the intersection, we need the probability of the conditional or the conditional probability. And I need to times it by something. What do I want to times it by?
Given.
Okay. The probability of the given thing, so the HIV. So for intersections, we always know we're multiplying. So we find our conditional probability and multiply by the given. So 0.999 times 0.006. Point 0.05994. So notice it is really close to our 0.006, which makes sense, but just a little bit smaller. So the probability that any randomly chosen American has HIV and gets a positive test result is 0.005994. Now this next part is why we actually care. Okay. So the test isn't perfect, so sometimes you have HIV and you get a negative test result, and sometimes you don't have HIV and you get a positive test result. Okay. So what we really care about is we don't really care so much about if we know you have HIV, what's the probability you get a positive, because then we already know that they had HIV. That's not really that interesting to us. What we really want to know is if you get a positive test result, what's the probability that you actually have HIV? Okay. Any guesses on what that probability might be? Sort of ballpark?
HIV given you have positive test. No.
Yep. So we're trying to figure out the probability that you actually have HIV if you get a positive test result. So that's what we're really interested in. Okay. So what do you think? So you think really close to 1? Okay. So let's try it out and see. Okay, do you have a formula to find the probability of find a conditional probability? We know that we need to do the probability of the intersection divided by what probability? We divide always by the given probability, so divide by the positive. And we just found the intersection up above. And the probability of positive is 0.016. And it gives me 0.374. Okay. So if you get a positive test result, the probability that you actually have HIV is 37%. Does that seem shocking to anyone? Okay. So a lot of people, they see this and they say, okay, well, 99.9% accuracy, that sounds really good. And then they realize the probability you actually have HIV, if you know you get a positive test result, is only 37%. And this is a cool phenomenon that happens when you have a very low probability or when it's a very rare event. So it's very rare to actually find someone with HIV. And so because of that, just the fact that so many people are taking the test and different things like that, it ends up being that you actually have not as good of accuracy as you thought you did. This is kind of an interesting thing that we always put this in any statistics class. Throw that problem in there. But let's look a little more at the mathematics now. So notice we started with the probability of positive given HIV, and through our different steps, we found the probability of HIV if you already know they're positive. And we can go through and combine the steps. So when we found our conditional probability, okay, we did the probability of the intersection, but to find the probability of the intersection, remember we had to do our multiplication rule. So this formula was these are the actual steps we had to do to find our conditional probability. And Thomas Bayes in the 1700s discovered this shortcut formula, and he said rather than going through the two steps, I can jump straight to this step every time. And so we get Bayes' theorem, one of our most famous theorems. Okay? So it's the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. This is very useful when you want to kind of like switch your conditional probabilities. So if you know A given, or if you know B given A and you want to find A given B, etc. Now again, you know all the steps to do this the long way. Okay? Or you can use the shortcut formula of Bayes' theorem. So let's try Bayes' theorem. So there's a rare subspecies of beetle, 0.1% of the entire beetle population, that usually has a specific pattern on its back. Okay? And in fact, 98% of this rare subspecies actually has the pattern. Unfortunately for the entomologist trying to classify the beetles, some of the common beetles also have this pattern. Overall, we know that a total of 5% of all the total beetles have this pattern. And if an entomologist finds a beetle with the pattern on its back, what is the probability that it belongs to the rare subspecies? So let's go through and write down all the information that they gave us. Okay. So the first part, 0.1% of the beetle population. What is that telling me? That's the probability of what?
Of the rare subspecies.
Okay. So probability that they are the rare, 0.001. Let's see, the next thing is 98% of the rare subspecies has this pattern. What is that telling me? It is a conditional probability. Pattern given rare. 0.98. And the last thing, 5% of all beetles have the pattern. So that's telling me probability of the pattern, 0.05. And then the final thing is we want to find the probability. So if we know they have the pattern, what's the probability that they are the rare beetles? Okay. Do you see how this is useful? We know one conditional probability, but we're really more interested in the other conditional probability. So we want to use Bayes' theorem to find this. Okay. So looking up at the previous page, what do I need to write down? How do I translate my A's and B's into rare and pattern? Okay, I will write it at the top of the page for you. Okay, so this is our formula. So I need to start with my conditional probability. So the other conditional probability is pattern given rare. Okay, now times the probability of, let's see, so this was an A, so these two should match. So if this is rare, then this should be the probability of rare. Over the probability, so this was the B, that matched my given in the first thing. So pattern, so this is probability of pattern. Okay, and now we just plug everything in. So probability of pattern given rare is 0.98. Probability of rare, 0.001. And probability of the pattern is 0.05. So it's 0.0196. So 1.96% of beetles with the pattern are rare. So just finding the pattern ends up not being the best indication of whether or not they are rare. Questions at this point on Bayes' theorem? So for our last problem in this section, we are going to do the HIV problem again, but we're going to give you the information in a different way. This is actually probably the more common way to do a Bayes problem. So let's see. They tell us that 6.6% of the American population has the HIV virus. So the probability of HIV equals 0.006. Okay, well, they told us that last time. Let's see. A diagnostic test is used to attempt to know whether or not they have HIV. According to historical data, 99.9% of people with HIV receive a positive test result. So that means the probability of a positive, if you have HIV, equals 0.999. Okay. And then they tell us 1% of people who don't have the HIV receive a positive test result. So the probability of a positive, if you don't have HIV, equals 0.01. Okay. Notice that they give us different information than last time. Okay. So they gave us different information, and we don't know the probability of the positive anymore. Okay. And at this point, at least for me, it would be kind of difficult to just go through all the formulas that I know to try and figure out what the probability of positive is. And so it's a lot easier if I just do a tree diagram. So to start off with, you either have HIV or you don't have HIV. Okay. And the probability of HIV is 0.006. Probability of no HIV would have to be 0.994. And then after you have HIV or don't have HIV, you can get a positive test result or a negative, and then get a positive or a negative. And if you have HIV, what's the probability of getting a positive? 0.999. Okay. Which means the probability of a negative, if you have HIV, is only 0.001. Now the next thing they tell us is the probability of a positive if you don't have HIV is 0.01. So no HIV, then the probability of a positive is 0.01, and so then the probability of a negative must be 0.99. So the probability of HIV and positive is this 0.006 times 0.999 gives me 0.599, well, 0.005994. Does that number sound familiar? Okay, we found that last time. Is it easier to remember that you need to multiply those numbers if you have the tree diagram, or if you just try and think it through with the formula? Probably depends on who you are. The probability of HIV and negative, we need to multiply 0.006 and 0.001. 0.00, it's 6 times 10 to the negative 6. And then the probability of no HIV and positive, .00994, and probability of no HIV and negative, .98406. Now at this point, I mean, there is the formula that we're going to get to in a minute that you could use for Bayes' theorem, but I really like to just, on all of these problems, so you don't even ever have to memorize Bayes' theorem. You can always just draw a tree diagram and go through the one formula you have to memorize. So the only formula you really have to memorize is the conditional probability. So if we want the probability that they have HIV if they get a positive test result. Okay, the conditional probability formula says just do the probability of HIV and positive over the probability of a positive. Okay. So again, this is the only formula that you really have to memorize, and then if you do a tree diagram, you should be able to find your way to each answer. So looking at the tree diagram, the probability of HIV and positive is .005994 over, okay, and now I need the probability of a positive. They didn't give us the probability of positive, but how can I find it with my tree diagram? Just find everything that has the positive and add up those probabilities. Okay. So my .005994 plus .00994. So I just added up the two probabilities that had a positive. So 0.376. Okay, is that the same thing we got last time? Okay, yes. So again, this is typically how they do it. They just make it a little more complicated. But all you have to do is memorize this one formula and do a tree diagram, and you should be able to get through every Bayes' theorem problem with a lot less headache than I had when I tried to learn it the first time many years ago. How do you feel about Bayes' theorem for tree diagrams? Okay. Just remember, think through logically instead of trying to memorize lots of really complicated looking formulas. So when I teach Statistics 2000, which is the lower level, less mathematically inclined, I don't even teach Bayes' theorem. I just tell them, here's a tree diagram, here's the problem, go do it with what you know, and they can do it. Okay? You guys are statistics for scientists and engineers, so you get a little more theory. Okay. So here's some of the theory behind what we just did. You have what's called the law of total probability. Okay. So remember we talked about a partition? You really probably don't remember a partition, but a partition is when you take the sample space and you divide it up into events A1 through AN. And remember the rule is each of the events have to be disjoint. So each outcome is in one and only one partition. Okay. So if you start with your partition, and now you want to consider an event B. So B is my circle. So how do you think you could find the probability of B? Okay, so find the intersection B and all the A's. So we could find like that intersection, and we could find this intersection, this intersection. What am I going to want to do with each of these intersections once I find them? Add them up, okay. Would it hurt anything if I accidentally added up, try to find the intersection of this one? What's the intersection of this event and B? 0. So if I add that into my formula, is that going to mess me up? No. Okay, so I just need to find each of the intersections, and when I'm done, add them up. So we could find probabilities of B and intersections with AI and add them up. Okay, so we just intersect B with each of my individual events, add them all up. It ends up being a pretty cool rule if you're trying to prove everything that we do in statistics. Now this means, so if we actually want to write out in symbols, so if we have our partition of our sample space, then the probability of an event B is you just add up the probability of each of the intersections. So intersect it with A1, intersect it with A2, A3, all the way up to AN. Remember we said if it doesn't actually overlap, say like A7, that's okay because the probability of the intersection is just 0, so we can still leave it in our formula. Okay. So you can write it with intersections, or you can write it with conditional probabilities. So like the probability of A1 and B is just the probability of A1 times the probability of B given A1. We know that, so we can write it with these conditional probabilities. Okay. Again, these are formulas that you don't have to memorize. I'm not that mean. Okay. Which means that we do have a general form of Bayes' theorem. Okay, so we can rewrite Bayes' theorem using our law of total probability. So we can use our intersections, okay, or we can use our conditional probabilities. And really, I'll let you read through those on your own time. Just remember what I said, draw your tree diagram, memorize your one formula, and you're good. In fact, good enough that I don't think we need to do example 17 in here, but I will do it at home and post the video on the Canvas page in case you felt like you needed example 17 as well. But it's just the same thing we've done with our tree diagram and our formula. So we will skip this video on Canvas. And now we get to section 1.7, counting techniques. Okay. So this is counting techniques. I promised you a while ago that we were going to get to this eventually. Okay. So we're going to talk about like permutations and combinations. Again, not all of you might have had it in high school, but I do know it's usually taught. Like I had to teach it to my 8th graders for pre-algebra. So you've probably seen permutations and combinations at some point in your life, whether or not you remember it. So counting techniques. We're going to start with the multiplication rule, also called the fundamental counting principle if you're trying to look it up online. So if you have an experiment with k components for which the number of possible outcomes are n1, n2, n3, etc., then the total number of experimental outcomes, what you do, you just multiply them. Okay. So it's easiest to just see the example. Jill has 4 pairs of slacks, 5 dress shirts, 2 shoes, and 3 jackets that are suitable for job interviews. So how many outfits does she have that are suitable for job interviews? Okay, a lot. You could do the tree diagram and put out all the possibilities, or what can we do with these numbers? Just multiply them. So 4 times 5 times 2 times 3 gives me 120 possible outfits that she can wear to her job interview. So that is the list of every possible scenario. Or for our next example, if a store has 3 DVD players, 23 televisions, and 7 types of speakers, how many possible ways can they select their home entertainment center containing a DVD, TV, and speakers? So again, we just multiply them. So 483. That's the different ways that they can make their entertainment system. At this point, you've probably figured that out kind of intuitively as you did your tree diagrams. Like if I have hearts or not hearts 3 times in a row, then I have 2 times 2 times 2, so 8 possible combinations. The next thing we have is drawing objects with replacement. So let's say you need to choose a 4-digit pin. You can choose any digits from 0 to 9 with replacement. So how many possible pins are there? Okay. So how many possibilities are there for the first digit?
10.
How many for the next digit? The next one, 10. The next one, 10. So this is 10 to the power of 4. So 10,000? Okay. That was with replacement, so we put each number back. And we can generalize that formula, so if you ever want to draw so many objects from your total pool, then there are just n times k. So we had 10 items in our pool. We wanted to draw 4 of them, so we had 10 to the power of 4 possible ways to draw it. Okay? You can memorize this formula, or you could just think through it each time like we did in the example. Drawing objects without replacement. So you need to draw or choose a 4-digit pin. You can choose any digits from 0 to 9 without replacement. So you can't use the same thing twice. How many possible pins are there now? How many choices do I have for the first number?
10.
Then
9.
Then 8. Then 7. So that is 5,040. That actually narrows it down quite a bit, doesn't it? So as far as privacy concerns, would you rather have pins where there's more possibilities or less possibilities? More possibilities. So it turns out, just like we could generalize our formula up here, where we did 10 to the power of 4, we can also generalize this formula, our 10 times 9 times 8 times 7. Okay, and the way that we do that is we just start, so we start with the number of objects, times by 1 less, times by 1 less than that, times by 1 less than that, and keep going until we have the number of objects that we need. And it'll end up being that the last one is n minus k plus 1. Okay. Again, you probably don't want to memorize it, you probably just want to think through it like we did in the example. But you know mathematicians love formulas, and so why not come up with a formula for it? Because if you get something like 10,000 options and you want to choose 500 things, you probably don't want to sit there and multiply that out in your calculator. So we start with what's called a factorial. So if n is a positive integer, we define n factorial to be n times n minus 1 times n minus 2 all the way down to 1. And we also define 0 factorial to be 1. Partly because mathematicians, the one that invented it, declared it to be so, and also because it makes sense logically in our story problems that we do with this. Our permutations, okay, so this is the one formula that you do need to know. So we use a permutation when we want to select k number of objects from a total n objects. We are selecting the objects without replacement, so we don't put them back, and the order of the objects matters. So that means that getting a pin 0, 1, 2 is different from getting a pin of 2, 1, 0 or 2, 0, 1. So the order matters. So the number of possible permutations, and so that means all of the possible scenarios we can come up with if the order matters and we don't replace them, is n factorial over n minus k factorial. And we use the notation p with the little n and the little k. Okay, how many of you have that on your calculator or know where it is? Okay, where the permutation is. Or the factorial. Factorial should be on everyone's calculator somewhere. Okay.
89 is diamond divide.
Okay. Diamond 5. What's the diamond? Oh, the second. Oh, diamond divide. I didn't know that. Good to know. Okay. I have a button on my calculator that says NPR. Okay, a lot of you on the TI family, you're going to be looking for math or probability options, and they should be in there somewhere. Some of you might not have permutations, and you have to use the factorial buttons.
So we're supposed to have the P and K on the factor?
You might have it on there. You might just have a factorial. If you want to bring up your calculator after class, I can look at it and see if I can find it on there.
It's probably been 89, I think.
I know it's on the 89. Who just said that it was diamond and divide on the 89?
That's factorial. Sorry.
Oh, that's factorial.
If you go to catalog on the 89, it's NCR and NPR. NCR and NPR.
And otherwise, if you get to the math, it's like second, math on the 5, and then it's under number 7 for probability. You have a factorial and NPR and NCR on the 89s. So, again, there's lots of different calculators to play with yours, and also you can bring it up after class, and I've played with enough over the years I can probably find it for you. So let's, while you're thinking about your calculators, let's do example 23, and then we'll go back to example 22. So we have 16 tennis players compete in a tournament, and how many ways can the rankings for the best 5 players be assigned? Okay. So let's think about it. So we want to select 5 people out of our total of 16. Okay. Should it be without replacement? You're not going to assign the same person a first and second, are you? Okay. So it's without replacement, and the order does matter. So we're doing rankings. So John first, Julie second is different from Julie first, John second, right? So this fits our permutation. So we want to see how many ways can it be arranged. So this is going to be a permutation. We have 16 total. We want to choose 5. Okay. If you can find it on your calculator, this is a good time to try it. I'm going to write out the formula. So this is 16 factorial over 16 minus 5 factorial.
So how do we do that with NCR and NPR?
Okay. Depending on your calculator, okay, in the TI-89, I would do 16, 5, right? So TI-89 is 16, 5. On my other calculator, I actually do 16, then push my NPR button, and then put in my 5. And either way, I get my answer.
You see because...
Sorry, did I say C? I meant to say P. NPR.
So what's the criteria to distinguish between the two?
Between C and P? I will tell you that in like 3 minutes, if I can. Okay. And if you happen to have just the factorial button and you have to do it that way, you can as well. But you put it in your calculator and you get 524,160. So who would have thought that if you had 16 tennis players and you're trying to pick out the best 5, there are actually 500,000 different permutations that you could come up with. Aren't you glad I didn't make you do a tree diagram?
Yeah.
Good. So let's while we're here, just because this is a cool thing mathematically, let's show that our formula, okay, this n factorial over n minus k factorial, is equal to our previous formula. Remember when I wrote this up above on the previous page? So we actually did the permutation formula by hand without realizing it, and we're going to show now that this is actually equal to it. So let's start with n factorial over n minus k factorial. So n factorial, when you start writing out n factorial, you do n times n minus 1 times n minus 2, dot, dot, dot. You're going to get down to n minus k. What would be the next thing? Actually, let me go up a little bit. N minus k plus 1. Then the next one would be n minus k. What would the next thing be? N minus k minus 1, dot, 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 all the way down to 1. Okay, so you just keep going down. So 1 lower, 1 lower, 1 lower. Now if I want to do n minus k factorial, I start with n minus k, and then times it by the next thing that is just 1 lower. So what is 1 lower than n minus k?
N minus k minus 1.
N minus k minus 1, then n minus k minus 2, dot, 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 down to 2, to 1, etc. Okay, now what do you notice about this? Okay, they're going to start canceling. So there's n minus k, n minus k, n minus k minus 1, dot, 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 everything cancels from the top and bottom. And we're left with n times n minus 1 times n minus 2, all the way down to n minus k plus 1. But luckily we have our calculators to do this for us. So let's look now at combinations. Okay, so we use in combination when we want to select k objects from the n objects. We're selecting the objects without replacement, and the order of the objects doesn't matter. Okay, so how does a combination vary from a permutation? Okay, the order doesn't matter. So you asked me what's the difference between my NPR and my NCR. Okay, and it's whether or not your order matters. So if order doesn't matter, you look at a combination. Okay, so the number of possible combinations, so C, that N, K. We use this symbol a lot. So this is N choose K. You might even see this symbol somewhere on your calculator. We read this N choose K. Is n factorial over n minus k factorial times k factorial. So again, we use this when our order does not matter. So suppose you want to draw a hand of 4 cards. The order you draw the hand in doesn't matter. How many possible combinations are there? Okay, from a standard 52 card deck. Okay, so how many total cards are there? 52. The order that I draw them in doesn't matter, so it's a combination, and I want to choose 4 of them. So I could also write this as 52, choose, there's no fraction line, 52, choose 4, or this is 52 factorial over 52 minus 4 factorial times 4 factorial. Put it in your calculator. 270,725. Okay, so this is a picture in a game where you just draw 4 cards, put them in your hand. There are 270,000 combinations of cards that you could have chosen. questions to hear? Then let's practice actually going through the problems and picking out what we need for each problem. Okay, so this is where they're all mixed in together, so you get a better practice. So we want to find the number of possible choices for each scenario. So a garage employs 7 mechanics, and 3 are needed on this one particular job. And how many ways can the assignment be made? Okay, so sometimes you're going to have to think through it logically and say, well, okay, do I think the order matters here? Okay, I would think that the order doesn't matter. Okay. So order doesn't matter. So is this a permutation or combination? Combination. So this is a combination. My total is 7 mechanics, choose 3, or 7, choose 3. Put in your calculator. I get 35. So
Tess, would you specify if order does and does not matter?
It could be problems kind of like this, where I might say it, or it should be fairly obvious, I would think. I try to make it seem obvious to me. Okay. So like the next example, at a rural high school, class officers are selected from a senior class of 50 students. How many different ways could a president, vice president, secretary, and treasurer be chosen? So in this one, it should be obvious. Should this be, or this is one that I could put on there and some would be obvious. Should it be ordered or not ordered? Order does matter. So this is an order one. So do we want a permutation or combination? Permutation. So we have 50 total students. We need to choose 1, 2, 3, 4 of them. Order matters. So there are actually 5 million ways that you could choose your student body officers out of only 50 students, if they all read. Now this is assuming that John is president, Julie is vice president, Stacy is secretary is different from Stacy, John, Julie, etc. Now let's change this. So suppose the senior class is governed by a committee of 4 officers of equal rank. And how many ways can the committee be chosen? So this now becomes something where order does not matter. So we're going to use a combination. And now there are only 230,300. Why is it so much lower?
Because it's the same for people might be like in a different order, but because order doesn't matter, there's an option.
Yep.
Also,
Okay, you sure?
yeah.
Okay. So for my next one, we have a high school basketball team with 15 players. If 5 players are on the court at any one time, how many different possibilities are there? And it tells us that we have learned how to play different positions. So they do know how to do a guard, forward, etc. Okay, so what do you think this one should be?
Order does not matter.
Okay, so this one, order does or doesn't matters. Okay. Well, so if one person's a guard and one person's a forward, doesn't matter if you switch the positions. Is that going to be a different possibility?
It's the same set of 5 players.
Okay. So I guess this is one that I would not put on the test because I guess it's not obvious. So for me, okay, so if you read 4 and 5, between 4 and 5, which one sounds like order should matter more? Okay. Okay, so I think order matters in 4. So again, John is forward, Julie's guard is different from Julie's forward, and John is guard, right? That would give you different combinations. People are going to play differently in different positions, so you would have different combinations technically. So I think this one is one where the order matters. So I was going to do a permutation here. 360,000 combinations. So the coach gets to try and go through each of those to try and figure out which one's the most optimal combination, right? Okay. Whereas number 5, they don't know how to play positions yet, so it's really just 5 people out there on the court at a time, so order doesn't matter. So it's going to do a combination. So 3003. So I have that John is working on his magic tricks. He pulls a card out of a standard 52 card deck, looks at it, and puts it back. He does this 6 times. How many possible sequences of cards are available? What do I need here? Okay. The order matters. Okay. Is it a permutation? Okay. Go back and look at the qualifications for the permutation up above. Okay. Is there anything on that is not satisfied with this problem? Okay. So for permutation, it has to be without replacement. What do we have here? This is with replacement, so it's not a combination or permutation. So you'll have to pay attention to that. So if we're looking at 6 cards, okay, how many cards does he have to choose from the first time? It's 2. And the next time? And the next time? The 4th time, the 5th time, and the 6th time. So I get 52 to the power of 6. And again, this is different from a combination or permutation because we didn't we put the cards back, so it's with replacement. So it's 1.977 times 10 to the power of 10.
How would that be different if order didn't matter? Or we could do that?
We're actually not going to do that one in this class because it's a more complicated formula. Okay, but it is out there. It's just we don't usually do it till a 5,000 level class. Make you memorize that one.
Is that to the 10th power?
Yes. Now this next part is what kinds of things you'll actually see in your homework. Okay, we'll see some of the basic ones and then they get a little bit harder. So suppose we have 9 out of 500 chips in a box are defective and 3 chips are sampled at random from the box without replacement. Okay. So first of all, what is the total number of possible samples? Now on the test, I'll try and be more specific and say order matters or doesn't matter. Your homework isn't always that specific. Okay, looking at this one though, like if you're just pulling out 3 chips to see if they're defective or not, do you think the order matters? Okay, so I'd guess order doesn't matter. And probably if they don't say otherwise, you can probably assume that order doesn't matter. So we'll say order doesn't matter. Okay, it's without replacement, order doesn't matter, so we can use a combination. What's my total number?
500.
And how many am I sampling? So 20 million different samples I could choose, and that's with order not mattering. So now I might ask you something like, what is the probability of choosing 3 defective chips? It is going to be pretty low. Okay. Let's see, we know the total number of possible samples. So if I want the probability of choosing 3 defective chips, that means each of the chips must be defective, right? So I could do something like, okay, so I just really need to figure out the total number of chips, or ways to get 3 defective chips, and divide it by the grand total. Okay. So how many ways can I choose 3 defective chips? Thoughts? Go ahead and brainstorm. What? So think about that way, or like just keep thinking, so how many ways can I get my 3 defective chips?
Well, we're only picking 3 isn't the only one.
Okay. It needs to be defective, 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 but which of the 9 chips gets to be the first defective, and which of the 9 chips gets to be the second defective, and which of the 9 chips is the third defective? Okay, so if you're really thinking of how many ways can I get my 3 defective chips, well, I have 9 defective chips and I need to choose 3 of them. Okay, is the way that we're going to think about it. So we're going to do the combination of 9 and 3. Okay, so to get 3 defective chips, there are 9 choose 3 ways that you can get your defective chips. Because we're not like doing probabilities here of the first one's defective, the next one, and the next one. It's easier to just think, okay, well, how many ways can I get 3 defective chips out of my total number of samples? So it's 84 out of the 20,708,500. So 4.05 times 10 to the negative 6.
So why would I try it a different way and have put like I got
The same answer.
4.03 to the negative 6, and I did 9 divided by 500 times 8 divided by 500 times 7 divided by 500. Is that correct too? It's a little off.
Did I? I don't know. Okay. Okay. So, well, let's actually switch to the board for a minute. Actually, we don't switch to the board. I have a blank paper on here. So, ouch. You are right that we can do it that way.
Oh, never mind. I just did change the denominator. You get the same thing.
Okay. Well, and let's see why you get the same thing. So we were used to doing them with the probabilities, and then this is just kind of changing a little bit to show you how you can do it with combinations. Okay. So we ended up saying that this should be 9 choose 3 over 500 choose 3. Correct? So let's figure out and actually write out what this really is. Okay. So use your formula. So this is 9 factorial over 3 factorial times 9 minus 3 factorial over 500 factorial, 3 factorial, 500 minus 3 factorial. And now we're going to use our math skills, since you should all have them in this class, to simplify this. So this is a complex fraction. I end up getting 9 factorial times 3 factorial times 500 minus 3, so 497 factorial, over 3 factorial, 6 factorial, 500 factorial. Everyone good? You're my people that make sure I don't mess up. This 3 factorial, that 3 factorial are gone. Let's do this. Simplify. It's 9 factorial over 6 factorial times 497 factorial over 500 factorial. Okay. So 9 factorial. This is 9 times 8 times 7 times 6 dot 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 times 2 times 1 over 6 times 5 times 4 times 3 times 2 times 1. Okay, so what happens here? So those are gone, right? I guess I don't know how to add another page onto this. And okay, so at this point we had our 9 factorial over 6 factorial times 497 factorial over 500 factorial. Okay, and so we got that this was 9 times 8 times 7. Okay, now let's work on the 497 over 500. So 497 factorial is 497 times 496 down to 1 over 500 factorial is 500 times 499 times 498 times 497 Okay, so what's going to happen? 497's cancel. So we're at 9 times 8 times 7 over 500, 499, 499. Okay. Now, tell me, yes. Okay. That would probably affect our rounding, right? Okay, so you wanted to do it a different way. Tell me your logic on how you did it with the probabilities. Okay, so you thought about the tree, so you said the first time to get one defect on the first time, the probability would be 9,500. Okay, the next time the probability of getting a defect is 8 out of 499. The next time the probability is 7 out of 498.
What is that? Is that including like getting a defect each time? Are you getting a defective chip every time you're pulling there?
Yes, so this is saying on the first draw I get a defective, second draw I get a defective, third draw I get a defective. Because we did want 3 defectives, which means each one has to be defective. So isn't it nice that using our first method and using our second method we get the same answer? Okay, so you get to usually choose what will make the most sense to you. So number 3, what is the probability of choosing an example that has a sample that has exactly one defective chip? Okay, how could you do this? You could draw out your tree diagram. You're choosing 3 chips, so each chip is defective or not defective, so you're going to have 8 total branches. You could find the probability for each one, and you can go through and say, well, this one has 1 defective chip, this one has 1, this one has 1, and add up those probabilities. Okay, or we can try it with the combinations. So I still know that I have a total, that's still my total number of chips overall. Okay. What's the probability of choosing a sample that has exactly 1 defective chip? So this is the way that we're thinking about it with combinations, as we say, okay, I want 1 defective chips. How many defective chips are there? 9. So there are 9 defective chips. Okay. But I need the first chip to be defective, and then what do the other chips need to be now? Non-defective. How many non-defective chips were in there? 491. And how many non-defective chips do I need to choose out of that bag? 2. Okay, so I first have to get 1 defective chip, of which there were 9. And then I say, okay, well, I need now 2 non-defective chips. There were 491, and I needed 2 of them. Okay. Now, in case you were wondering, does anyone want to write it like this? So I needed to choose 1 defective chip, so I had 9 defective chips, and I needed to choose 1 of them. Put in your calculator, what is 9 choose 1? Just 9. So you can think of it either way. So this is really 9 times 491, choose 2, out of our total of 500, choose 3. And we put that in the calculator. .0522. Again, you could do this with a tree diagram, but it's going to take you a little bit longer. So if you figure out how to do it with the combinations, it might help. So, questions on probabilities and combinations, or permutations and combinations.